Hi. Composite functions are a different approach to combining functions. A composite that has a definition in the dictionary of being made of distinct elements or materials. So composite functions are functions that are actually created by replacing the independent value, which is usually the x, in one function with another complete function. What if we let f of x equal, say, 2x plus 3, and g of x equal 7x squared minus 5. Now, the notation to mean compose two functions together is a little circle, a small open circle. Now, I know this looks like fog. That's okay. Sometimes it puts people in a fog. Anytime you see f composed with g of x, rewrite that with just the parentheses. It means f of g of x, which means that we're going to replace the x in f of x with g of x. Now, in this particular case, g of x is 7x squared minus 5. So let's color code this a little bit. What if we let g of x, I'm going to do g of x in blue. So we know that g of x is 7x squared minus 5. Now f of x, since f of x is 2x plus 3, then you know that f of 3 would be 2 times 3 plus 3, which would be 6 plus 3 is 9. F of 0 would be 2 times 0 plus 3, which would just be 3. F of z would be 2 times z plus 3. No way to simplify that. So essentially, f of anything means multiply 2 times that anything and then add 3. Well, now we want to find out what f of g of x is. And since g of x is 7x squared minus 5, then f of 7x squared minus 5 is just going to be 2 times 7x squared minus 5 plus 3. And then I could put the combined function maybe in green. So that's going to be 14x squared minus 10 plus 3 would be 14x squared minus 7. So the circle means composition. It means, rewrite it like this. The second function is going to replace the x in the first function. What if we have f of x is 5x plus 2, g of x is 2x squared minus 4x minus 1, and we are asked to find f composed with g of not necessarily x. What if we have, I don't know, how about 3? To find f composed with g of 3, first of all, you want to rewrite it like this. That means f of g of 3. So there's different ways to do this, but the first thing we could do would be to find g of 3. And then we will proceed to plug g of 3 into f. G of 3, well, g of anything means 2 times your anything squared minus 4 times your anything minus 1. The x is nothing here but a placeholder. So g of 3 is 2 times 3 squared minus 4 times 3 minus 1, which would be 2 times 9 minus 12 minus 1, 18, minus 12 and minus 1 is minus 13. So g of 3 is 5. So f of g of 3 is 5. So now we're going to plug 5 into f. Well, f of anything is 5 times our anything plus 2. So f of g of 3 is the same thing as f of 5. And f of 5 is going to be 25 plus 2 is 27. Now notice that if we were to find g of f of 3, that is most likely going to be very different. First of all, we want to find g of f of 3, which is going to be g of, well, f of 3 is going to be 5 times 3 plus 2, which is 15 plus 2 is 17. So g of f of 3 is the same thing as g of 17. G of 17 is going to be 2 times 17 squared minus 4 times 17 minus 1. Let's do a little math here. 17 squared is 289. 17 times 4 is 68. So this part is going to be a minus 69. 289 times 2 is 578, and 578 minus 16. Oop, hit a wrong button here. Sorry, a few technical problems there. So 578 minus 69 is 509. So f of g of 3 f of g of 3 was 27. G of f of 3 is 509. It's normal that they are not going to come out the same. If they ask you to just find f of g or g of f of a number, then the easiest thing to do of some kind of a constant value, just a regular number. Find the value of the constant in the second function listed. This one. Go ahead and simplify. And then plug that into the first function. Now, if they want you to do, I'm just going to write out one of them, f of g of x here you have to actually plug g of x into f in place of all x values. And simplify. And you want to really watch out for foiling situations. That's a big red flag. For instance, what if we had f of x equals x minus 7? G of x equals x squared minus 3x plus 2. If they ask us to find f of g of x, which is going to be f of g of x, which is going to be f of x squared minus 3x plus 2. So we plug this in place of the x in f. We're plugging it into f, so recall that f of whatever means whatever minus 7. We don't really need the parentheses here. And this might be a little distracting. So f of x squared minus 3x plus 2 would be x squared minus 3x plus 2 minus 7. All f does is tells you to subtract 7 from whatever x is. So in this case, our x becomes this whole function. So it's just going to be x squared minus 3x plus 2 minus 7, which would be x squared minus 3x minus 5. Now, on the other hand, if they say find g of f of x, which would be g of f of x, or g of x minus 7. Well, since g of anything is our anything squared minus 3 times anything plus 2, then g of x minus 7 is going to be x minus 7 squared minus 3 times x minus 7 plus 2. This has to be FOILed out. This means x minus 7 times x minus 7. This has to be distributed. Minus 3x plus 21 plus 2. So we've got x squared minus 7x minus 7x plus 49 minus 3x. Go ahead and combine these, would be plus 23. So we end up with x squared minus 7 and minus 7 and minus 3 would be minus 17x. And a positive 49 and a positive 23 would be plus 72. And once again, notice that they came out very differently. Now, we talked about domains the other day. Frequently, the domain of this is harder to figure out than doing it to start with. In this case, the domain is all real numbers. In this case, the domain is all real numbers. To find your domains of composites, composite functions, you have to start with the domain of your second function. It must exist to plug it in. You can't plug in something that doesn't exist. So anywhere the second function, the g of x, the one you're plugging in, or here the f of x, if that doesn't exist, then it cannot be plugged into the first function. So, and I know this is the one we're starting with, so it's kind of hard to say what's first and second, but I'm saying as listed. This is the first, and this one's the second. This is just for reference. So this function has to exist in order to be able to plug it into this function. So you start with the domain of g of x, or whatever the one being plugged in is. Then see what if any, additional restrictions get created. Not going to let me write there. In this case, where we're plugging in g of x, it exists all the place, everywhere, all real numbers. When we look at the composite function, the domain for this is also going to be all real numbers. So the domain here of f of g is all real numbers. Same thing happens on this second example. X minus 7 has no restrictions, so that's all real numbers. X squared minus 7x plus 72 has no restrictions. So here the domain is also going to be all real numbers. Let's look at an example where let's look at a couple of functions. Let's let f of x equal the square root of x and g of x equal x minus 3. Now the domain here, because in order to take the square root of x, we know that x has to be greater than or equal to 0. This is going to be bracket 0 to infinity. The domain here is just all real numbers. No restrictions. There's no radicals, there's no fractions. For f of g of x, we've got f of g of x, which would be f of x minus 3. So we plug x minus 3 in place of the x, so it's going to become the square root of x minus 3. For the domain, we have to start with 0 to infinity. It cannot be larger than that. The domain for the composite function cannot be, oh, I'm sorry. Wait, the inside is all real numbers. Getting carried away here. So we start with actually all real numbers in this case. Forgive me. The domain of g of x is all real numbers. In the composite function, because we have something in a square root now we have to also take into account that x minus 3 has to be greater than or equal to 0, which should be x is greater than or equal to 3. So we started out with all real numbers, but we have a new restriction in that x has to be greater than or equal to 3. So the domain for this becomes, for the composite function, becomes 3 to infinity. If we look at f of g of x, sorry, g of f of x is g of f of x. So it's g of f is the square root of x. So that's going to become the square root of x minus 3. We start with the restriction here that x has to be greater than or equal to 0 for the domain. Because that's the restriction here. Here it's going to be unchanged. The 3 is not in the radical, so the domain remains that x has to be greater than or equal to 0. So in a composite function, you're going to be plugging one function into the other function. Rewrite it in terms of the parentheses. For the domains, if you're plugging in a number, just find the numerical value of the second function and then plug that result into the first function. It's easier to just do that. You could actually find the composite function and then plug the number in. You'd get the same result. It's just usually more work. If you're going to leave it in terms of x, then for the domain, you take the domain of the second function, the one that's being plugged in. That's your starting point. It can never be larger than that. Any restriction on the second function that's being plugged in has to remain with the composite function. And then once you get the composite function set up, look and see whether there are any new restrictions. And those restrictions would come out of the domain from the second function. So they may create additional functions or restrictions, or they may not. We will be seeing you later. Good luck with this. Have fun. Just treat it like a new kind of puzzle, and it'll work out pretty well. Bye.